Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element bismuth. Bismuth is a brightly silver element. Let me magnify this for you, and I have a much larger sample than the normal vials I have. Check it out. It's beautiful, silvery, reflective. You can begin to see some of the crystals of this element as well. Let me go back to our slides, though. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Bismuth is the 83rd element in the periodic table. Its atomic number is 83 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Although bismuth was known prehistorically, it was not really recognized as an element on its own. Beginning in 1738, Johann Heinrich Pott, Torbern Olaf Bergma, and Carl Wilhelm Scheele began to suspect that bismuth was distinct from other elements it resembled, such as tin and lead. In 1753, shortly before his death at the young age of 23 or 24, Claude Francois Joffre finally proved bismuth was an element distinct from all the others. Since bismuth has been known since ancient times, it's a bit uncertain where it got its name. The word bismuth has been in use since the mid-1600s. It may have come from German Bismuth, or from a later Latin translation of that term, bismuthium. In any case, we now use bismuth. While bismuth does occur natively, such as the samples you see here, this is not the normal source of the element. Bismuth is often associated with the ores of lead, tin, and copper. However, its most important ores are bismuthinite, a sulfide, and the closely named bismuthite, an oxide. It's usually not economical to mine bismuth as a primary product. Rather, it's most often obtained as a byproduct of the processing of other metal ores, especially lead. Estimates are that in 2022, the world produced around 19,000 metric tons of bismuth. This is the United States Geological Survey figure for refinery output. 19,000 metric tons of bismuth would be a cube only 12.44 meters on a side. Let's throw an average person in there for comparison. Bolivia, Peru, Japan, Mexico, and Canada are thought to be leading producers of this element. Here's the refinery production of bismuth for the last 40 years. It seems to have stabilized over the last decade. I'm guessing the increase around the year 2000 is due to the banning of lead and the substitution of bismuth for many of these purposes. As we just saw, bismuth is a shiny silvery metal, but it's pretty brittle. Currently, bismuth is going for about $21 per kilogram. Like our previous element, lead, it's one of the cheaper elements we've seen so far. And, as usual, prices depend on purity and the quantity you buy. According to the United States Geological Survey, here's how the price of bismuth has varied from 1906 to 2011 in dollars per kilogram. As you can see, bismuth has varied quite a bit, between about $3 and $31 per kilogram, with spikes in the mid-1970s and in 2008 because of the financial crises in those years. Still, seems to be quite a bargain, even at today's high price. The element bismuth is pretty uncommon. Coming in as the 66th most common element in the universe by mass, it makes up 7 parts per 10 billion. About 14 times as abundant in the Sun, it makes up almost 1 part per 100 million of its mass and is the 34th most abundant element there. It's the 67th most abundant element in meteorites, 6.9 parts per 100 million. Curiously uncommon there. Surprisingly uncommon in the Earth's crust. It's the 71st most common element at 2.5 parts per 100 million. Silver is 3 times more common, but 47 times more expensive. Go figure. Bismuth is rarest in the oceans, making up only 2 parts per 100 billion, the 63rd most abundant element there. And lastly, like most elements in the upper reaches of the periodic table, there is no bismuth in us. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here, you see each element square with a tiny chart of its own showing that element's growth over the age of the universe by various processes. Bismuth is here. I understand this looks complicated, but let's look at just bismuth a little closer. The horizontal axis of this square represents time, from the Big Bang to now. The vertical axis shows the proportion of bismuth created by various processes relative to the Sun. About 34% of bismuth present today is believed to be produced by dying low-mass stars, the magenta area. 58% is produced in supernovae, the yellow area, and a small amount, that green icing on the top, represents 8% produced in neutron star mergers. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 83 protons for bismuth. But there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 36 known isotopes of bismuth, and of these 36, it was thought there was one non-radioactive isotope, Bismuth-209. However, in 2003, a team of French physicists confirmed that even Bismuth-209 was unstable, but just barely, as we'll see in the next slide. Even though Bismuth-209 is not technically stable, it still hangs around for a long time and makes up 100% of the bismuth you find today. The heaviest nucleus considered to be stable is lead-208. The word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of bismuth occupy the same place in the periodic table. Of the isotopes of bismuth, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest bismuth half-life is Bismuth-209, with an eye-watering half-life over 20 quintillion years. That's almost 1.5 billion times the age of the universe, which is itself currently 13.8 billion years old. If you had a large 1 kilogram block of Bismuth-209, less than 300 atoms a day would decay. And since Bismuth-209 decays by easy-to-stop alpha particles, only the decaying surface atoms of your kilogram would emit detectable particles. All the internal decays would be absorbed by the bismuth itself. A large block of bismuth metal seems less radioactive than it really is because it's self-shielding. If you want to experiment with the isotopes other than bismuth-209, they must be manufactured in a reactor. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1024 atoms of any isotope from the previous slide. I chose 1024 atoms because it's a power of 2, and we'll be doing a lot of dividing by 2. If you wait one half-life, 1/2 of your isotope will decay, and you'll have 512 atoms left. If you wait one more half-life, half of that half decays, leaving you with 1/4 of the original 1024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice there's one remaining atom after 10 half-lives. If you waited one more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Bismuth has a fairly high density at 9.78 grams per cubic centimeter. As a reminder, water has a density of only 1 gram per cubic centimeter, and I've put up more densities for you here. As you can see, bismuth's density falls comfortably between iron and lead. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, and magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, bismuth's density is 9.78 grams per cubic centimeter, the magenta circle. Given bismuth's low cost, a block of this stuff would be fairly inexpensive, only about $12. Maybe I should cast one. Its density sits nicely between lead and copper. Bismuth has a very low melting temperature of only 271 degrees Celsius, or 520 degrees Fahrenheit. It has the 26th lowest melting point, and 12 of those 26 melt below room temperature. You could easily melt this stuff on your stove, and many people have to create those beautiful and colorful crystals. Bismuth boils at a fairly low 1,564 degrees Celsius, or 2,847 degrees Fahrenheit, giving it the 66th highest boiling point, or the 34th lowest boiling point of all the elements. That's 1,293 degrees Celsius above its melting point, giving it the 52nd largest liquid temperature range of all the elements. One of the subscribers to this channel, SillySad3198, thought it might be nice to see a graph of liquid temperature ranges from highest to lowest. So here it is. The widest liquid temperature range is that of neptunium, with a 3,356 degrees Celsius liquid temperature range, all the way down to neon, which is liquid only in a 2.51 degrees Celsius range. Again, bismuth has the 52nd narrowest liquid range at 1,293 degrees Celsius, about in the middle of the pack. Notice all the noble gases, and hydrogen, have very small liquid temperature ranges. Speaking of thermal properties, bismuth has one of the lowest thermal conductivities of all the metallic elements. A couple are worse thermal conductors, but not much worse. Notice silver, copper, gold, and aluminum are the best conductors of heat. And since thermal and electrical conductivity usually follow each other, bismuth's electrical conductivity is also very, very poor. Here, too, Silver, copper, gold, and aluminum are the best conductors of electricity. Bismuth is one of the softer elements at only 2 on Mohs scale of hardness. It can be easily scratched, but soft does not mean malleable. You can't shape bismuth by hammering it. It shatters when hit. You might be able to scratch bismuth with your fingernail at hardness 2.5. Here's a chart of element hardness from hardest, boron, on the left, to the softest, cesium, on the right. We'll find bismuth here in the softer part of the chart, though there are a lot of elements softer than this month's. If we compare the size of the bismuth atom to that of hydrogen, we'd see something like this. The bismuth atom is about 2.7 times the size of hydrogen. Here's its electron structure. By the way, a picometer is a trillionth of a meter. Atoms are terribly small. Looking at all the element atom sizes, here we see them sorted from largest, cesium on the top left, to the smallest, helium on the bottom right. Bismuth has the 55th largest sized atom of the elements, about in the middle of the pack, between magnesium and zinc. Bismuth has a medium thermal expansion rate. As a matter of fact, it has the 23rd highest rate of all the elements, 1.34 parts per 100,000 per Celsius degree. This means if I had a 1 meter long bar of bismuth and heated it by only 1 degree Celsius, it would get longer by a bit more than 1/100th of a millimeter. That's slightly less than a hair width. But that's only heating it by a measly 1 degree Celsius. Bismuth expands about the same as gold and nickel. Bismuth and many of its alloys expand slightly when they solidify or freeze. This unusual property means solid bismuth floats on liquid bismuth. We don't think of this as unusual because we're used to the fact that ice floats on water. But this is not true of most other substances. The solid is almost always denser than the liquid. Silicon and gallium also have this property. This allows bismuth to fill all the corners of a mold to form a perfectly sharp replica when it solidifies. This is also a valued property when used in soldering or plumbing, the joining of pipes. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. Bismuth has a relatively simple visible spectrum. Let me increase the contrast to emphasize the lines. If you place bismuth salts in a flame, these are the colors you would see in a spectroscope. This spectrum uniquely identifies the element as bismuth to scientists. No other element gives off this set of colors. Let's take a look at a few applications of bismuth. At least one should surprise you. While not technically an application, beautiful bismuth crystals are fairly easy to grow, even at home. There are many YouTube videos showing you how. Fresh out of the pot, these crystals are silver, but they quickly begin to oxidize and form fantastic iridescent bubble-like interference colors. You can find these for purchase online or at many museum stores. Let me show you a sample. I have a beautiful museum quality sample here. You can see the beautiful iridescent colors. These are called Hopper crystals. But let's get back to our slides. Although pure bismuth melts at a pretty low 271 degrees Celsius, combining it with other metals can create alloys with even lower melting temperatures. These are called fusible or eutectic alloys. I've listed a few with their melting temperatures. Some melt below the temperature of boiling water, 100 degrees Celsius if you've forgotten. Low-temperature fusible alloys protect your buildings. Some fire sprinklers have two plates connected with low-melting alloy. When the temperature rises above a certain point, the plates come apart, releasing the water to put the fire out. Similarly, fusible links have cables attached to them. In a fire, the two halves melt apart, releasing the cables to close dampers and doors. On Thanksgiving, fusible alloys even protect your turkey from overcooking with those ubiquitous pop-up timers. There's a little bit of fusible alloy in the tip that melts at 165 degrees Fahrenheit when the turkey is done cooking. Shotgun shells used to contain lead shot. This seriously pollutes the environment with toxic lead, and let's face it, would you want to eat a bird that was infused with a toxic element? Bismuth or steel is now the preferred substitute. Moving to another sporting area, fisher persons used to use lead weights to keep the lines down where the fish swam. When a fish was caught, these weights would drop off the line, sinking to the bottom. Like the lead shot, this was, and still is, polluting the environment. Bismuth has been one non-toxic substitute, and the mild oxidation produces beautiful iridescent colors as a side benefit. Bismuth oxychloride is used in cosmetics, particularly in products like eyeshadows, blushes, and nail polishes, to provide a pearlescent effect due to the plate-like structure of its molecules. This was used back at least as far as the ancient Egyptians. It occurs in the somewhat rare mineral bismuth. In this sample, the bismuth oxychloride is the orangey-colored mineral within the larger stone. The rest of this mineral is bismuthinite, which we saw before near the top of the presentation. This device, called a Peltier cell, contains many bismuth telluride junctions and can be used to generate electricity in thermoelectric generators, as we'll see in just a moment. Making one side hot and the other side cool generates electricity. Interestingly, these also work in reverse. If you connect them to a source of electric current, one side gets hot and the other side gets cold. This is called the Peltier effect, named after French physicist Jean Peltier. These can be used to cool down small refrigerators with no moving parts, or you can use a Peltier cell to keep another component, like a CPU or a laser diode, cool and efficient. But back to its power-generating uses. Bismuth telluride thermoelectric generators are important for deep space missions like the New Horizons spacecraft that recently visited the planet Pluto. You can't use solar panels that far out. The sun looks like a very bright star in Pluto's sky. There's not enough light to generate electricity with solar panels. The electricity to run the spacecraft is generated thermally with a small nuclear power source, which supplies about 245 watts, at least at launch. As the spacecraft continues on its mission, the radioactive material decays, supplying less and less power until, in the late 2030s, the generated electricity won't be enough to power or heat the spacecraft. Same goes for the Mars Curiosity and Perseverance rovers. With both rovers' large power budget, solar panels won't do the job. It takes a lot of energy to do all that moving around, and you'll notice no solar panels here. You need a small nuclear-powered generator, here mounted on the rear of the rover. Curiosity's generator produced about 110 watts of power at the beginning of the mission. Here's the power generator waiting to be installed in the Curiosity Mars rover. It's called the Multi-Mission Radioisotope Thermoelectric Generator, or MMRTG. This is the stuff that makes it work. What you see here is a pellet of plutonium-238. not the stuff in the atomic bomb, which is plutonium-239. The pellet is not red hot because it was just taken out of an oven. It's red hot because it's so radioactive, the particle emission heats it to this temperature. 2 of these pellets are put into a cylindrical graphite impact shell, which also heats up to red-hot temperatures. And then 2 of those graphite impact shells are fixed inside a rectangular block called a general-purpose heat source. The purpose of all this is to keep the plutonium from escaping in the unlikely event the spacecraft fails during or right after launch, and the MMRTG falls back to Earth. There's a very good chance that these precautions will prevent the spread of any radioactive material. 8 general-purpose heat source blocks are stacked inside the MMRTG. The fins get rid of excess heat not needed to keep the spacecraft systems warm and to keep the cool side of the thermoelectric cool. Remember, you need a temperature difference to generate electricity. You see the bismuth containing thermoelectric module surrounding the hot plutonium heat sources here. There's research being done into the use of bismuth compounds as a fire retardant for PVC. This uses our familiar cosmetic compound, bismuth oxychloride, as a starting point. Currently, antimony oxide is used for this purpose, but has some environmental issues. Replacing this with the bismuth compound helps solve this problem. Bismuth strontium calcium copper oxide is a high-temperature superconductor. Don't get too excited. High temperature here means a maximum of minus 165 degrees Celsius, barely above liquid nitrogen's frigid minus 196 degrees Celsius temperature. You may have seen demonstrations of a magnet floating above a cooled superconductor, like you see here on the right. This is called flux pinning or quantum locking. Many substances glow when hit with ultraviolet light, but some also glow when hit with gamma rays. These glowing substances are called scintillators. These scintillators are all glowing by being hit from below with a large gamma ray source from cesium-137. This is a long exposure. Bismuth germanium oxide, also called bismuth germanate, gives off a tiny flash of light when hit by a gamma ray. This flash of light is cyan or blue-green in color. Moreover, the brightness of each flash is related to the energy of the gamma ray that hit the crystal. By measuring all the energies, you can build a gamma ray spectrum of the sample you're measuring, allowing you to identify the radioactive element. Bismuth-213, a daughter product of the decay of actinium-225, may offer some promising applications, including the therapy of leukemia, lymphoma, melanoma, brain and bladder cancer, neuroendocrine tumors, and prostate cancer. These isotopes are connected to appropriate molecules which attach themselves to the tumor. Injected directly into the tumor or into the bloodstream, the short-range alpha and beta radiation can deliver their therapies to the tumors and not affect surrounding tissue too badly. Most elements here in the upper end of the periodic table are terribly poisonous. However, we intentionally take this chemical, bismuth subsalicylate, orally and in significant quantities. You may know it by its more common name, Pepto-Bismol.
When you have nausea, heartburn, indigestion, unsystemic diarrhea.
Pepto-Bismol coats and soothes for fast relief when you need it most.
See the bismuth not so subtly hiding in its name? Although bismuth serves no known biological purpose, you don't need bismuth to survive, it's fairly non-toxic, as we just saw in the previous slide. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about bismuth. Given a half-life of 10 to the 19 years, de facto stable. In the next program in this series, I'll examine a notorious element used to kill spies, polonium. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element bismuth.